Assalamu alaikum dear students, we're back with another video lesson. In today's video lesson, we're going to talk about something totally different from what we've covered so far, and that is magnetism. Right? So what are the things we're going to cover in this chapter here? We're going to learn about magnetic field. That will be the first thing we're going to learn about. And then after that, we'll talk about magnetism from electricity. That would be inducing, creating, or producing magnetic field by using electricity or electrical current. And then after that, we'll talk about magnetic force on a charge or on a current carrying conductor, or you can say wire here. Now, to begin with, we're going to start with magnetic field first. Now, before we talk about magnetic field, first of all, we need to learn about magnets a little, then after that, we can talk about magnetic field. So what are magnets in general? We can say magnets are materials or objects that can attract iron-containing materials. Normally, magnets would have two poles, right? And these are called the North Pole and South Pole here. The reason why we call them North Pole and South Pole, because if you suspend them or hang them freely, they can rotate. And then once they rotate, they align themselves with the Earth's magnetic field line so that one of the side, all right, will always point north and the other side will always point south. That is, if it is not close to any magnet. So based on that, one of the side points north, the other side will always point south. Because of that, we call them north and south pole of a magnet, by the way. All right, so these are, we can say, the poles of a magnet, and this is a magnet. Once again, what is a magnet? It is a material, an object that can attract iron-containing material. It can attract, it can pull any object that contains iron here. Basha. Now, for magnets, we have two poles, and this is very important, and you need to know because it's also been in Uzadi as well. Basha. The question would be, for example, how many or what are the minimum poles of a magnet, right? Kamteen poli, what are the minimum numbers of poles for a magnet? That would be two, because no magnet, or we can never have a magnet with only a certain pole. So no matter how many times you break it down here, you could, for example, break down the North Pole here into a smaller piece in here. So every single piece will always have two poles, and these are going to be north and south, right? So we can never have a magnet with a single pole, by the way. So that is something you need to know. And also been in Uzadi as well. There's a chapter review question as well. It says, once you break a magnet into two, how many poles does each piece have? All right. Remember, each piece or each part of a magnet will always have north and south poles here. So that would be the minimum number of poles there. Now, there is one more thing here, for example. Now, we know that if we have magnets, let's say, all right, so what exactly or how do they interact with one another? Let's say there's north and south, or let's just, change these two for now, right? Let's say this is south, and then south and north in here, and then let's say south and north this time, north and south in here. So you can see that if we have two magnets, right, or like poles here, or you can say same poles here, they will always repel one another. Let me just change that one here for now, right? So if we have like poles here, you can see that south and south or north and north, they will repel one another. This is how magnets behaves once they are close to one another. But if we have unlike poles, what do you mean by unlike poles? Like, for example, north and south, right? North and south, then of course these two poles are going to attract one another. So based on this, we can say like poles, they repel one another, but unlike poles are going to attract one another. And there's one more thing you need to know. Magnets can attract or repel one another, but magnets can never repel an object that contains iron because it can only attract iron-containing material. So what are the things that magnet can attract? It can attract, for example, a piece of, let's say a paper clip, or it could be an iron nail. It could be any other things that contain iron, for example, right? It can be attracted to a magnet. So these are basically about magnet. We have something else which is also that is made of, or it is a magnet, and that is a compass. What is a compass, basically? Now we use compasses to, to determine the direction. So compass, obviously, it is made of, or it is a magnetic needle here. So this needle that you see inside a compass, it is magnet, by the way. But if this magnet can be pivoted, can be supported on something so that it can rotate freely, then this magnet, just like we've mentioned earlier, one side of this compass will always point north, and then the other side is always pointing south. So this is how we can use a compass to determine the direction north or south here. All right, but remember this: we can use a compass to determine the direction as long as this compass is not close to any other magnets, Basha. Because if it is not close to any other magnets, then this compass that is going to align itself with Earth's magnetic field line, which is something we're going to study later, Basha. Earth has also magnetic field line. Then it is going to align itself with the Earth's magnetic field line, so it will always show the direction north and south, or points, let's say, to the north geographic pole, geographic north pole, and then geographic south pole. This is how you can tell the direction. So once again, basically a compass, it is a magnetic needle that can, or once it rotates freely on a support, on a pivot, then it can show the direction north and south. Why is that? Because it aligns itself with the Earth's magnetic field lines here. All right, so these are regarding the magnets, all right, or regarding a compass here. Once again, Gutman, magnets can attract iron-containing material like what? Like paperclip iron or anything that contain iron in them here. And then we can also, there's one more thing here, we can magnetize, or magnets can magnetize objects too. What exactly does this mean here? So if we have a magnet, let's say we have north and south, by the way, magnets come in different shapes and size and strength, all right? So we can have small magnets, bigger magnets, or magnets that are stronger, or could be magnets that are weaker, and of course in different shape as well. This is a bar magnet, because it's a rectangle, you can say, or just like a bar. Let's say here, we could have a horseshoe magnet, for example, or other magnets that are rounded. Depends on difference. I mean, depends on what the magnet is or what is used for. But most of the magnets that we use, these are basically a bar magnet. So that's the only thing you need to know at this point here. So now going back to the point here, this magnet can magnetize objects. What exactly does that mean? If I have a piece of iron here, right, and you can call this one ferromagnetic material, by the way, this iron can become magnetized if it is inside the magnetic field of this magnet, or if you scratch this iron with this magnet, let's say several times here, right, then this iron also becomes a magnet, or can be, which after that we say it is magnetized. Now this piece of iron, of course, would have north and south pole. Now it can attract other pieces of irons here. So once this happened, we can say this iron is magnetized, or it became a magnet. So iron and cobalt are we can say two examples that can become magnetized. There are other, of course, let's say objects or materials too, but it's not mentioned in our book, so we're just not going to cover that. But otherwise, of course, you can use different, or you can magnetize some other different materials, and you can make them magnetize here. These are regarding, we can say, magnet. Now let's summarize what we have learned so far. We said magnets are materials that can attract objects that contain iron. Basha, magnets have two poles, and these are north and south pole. Very good. Now, what is the minimum number of poles for a magnet? It is always two. We can never have a single pole. Let's say a magnet with a single pole. There's always two poles, and these are north and south pole here. We also said that a compass is also a magnet, or a needle. Let's say a magnet that, of course, pivoted or supported on a pivot, so that it can, once it rotate freely, it can show the direction north and south. This compass should not be close to any other magnets, because if it is, then it can be affected by that magnet, then it can no longer show the direction north and south. And then we also said that like poles, like north and north, south and south, they can repel one another, but if it is unlike poles, like north and south, then they will attract one another. And we said also that objects can become magnetized too, right? All right, like iron and let's say iron and cobalt here. All right, so the next thing that we have is magnetic field. What is magnetic field here? Magnetic field. Magnetic field is labeled, all right, as B here, by the way. So what is magnetic field? We'll say magnetic field, there is a region around the magnet where magnetic force can be measured, or you can say detected too. So consider we have a magnet, by the way. This magnet has north and south poles here, as you can see here. There's this region around the magnet here that magnetic force can be detected or measured. That is what is called magnetic field. What exactly do you mean by this region? When we say a region, there is a space, Basha, a space around this magnet, or this area around the magnet, where magnetic force can be measured or detected. And how do we detect magnetic field? For example, let's say if you use a small piece of iron here, let's say inside the magnet first here, if it is anywhere here, it can be attracted, by the way, to the magnet, right? And by the way, both sides of a magnet can attract iron, so it doesn't matter which, right? Okay, so if it is a piece of iron at any point, no matter where it is, anywhere inside this, for example, or close to the magnet, it can be attracted. But if it is, let's say, somewhere here, then you can see that is not going to be attracted here. So because it is not affecting this piece of iron, we can say that this piece of iron is not inside the magnetic field anymore, because we don't see the effect of the magnet on this anymore. It cannot be detected. So that is out of the magnetic field here. Okay, but as long as it is close to any region here, then we can say this is inside a magnetic field. Magnetic field, by the way, it is a vector quantity. It has both magnitude and direction. And regarding the unit of a magnetic field, that is measured in what? It is measured in Tesla, and we'll just use the letter or capital T for the magnetic field here. The symbol of a magnetic field is B. The unit is Tesla. Don't forget this one. Now, regarding the magnitude and direction, we'll talk about this one in a second. But first of all, what is exactly magnetic field line? Because for magnetic field lines or magnetic field, we have some lines that represent let's say the strength and also the direction of a magnetic field line here. All right, or the strength and the direction, the strength, let's say, and also the direction of the field. What exactly these magnetic field lines are here, or how can we tell the magnetic field line around the magnet here? All right, so that would be the next thing. We said, remember, magnetic field has both magnitude and direction because it is a vector quantity. So how can we tell the strength or the magnetic field line or the shape? How does it look like and all that? Well, it's easy. For example, if you bring some iron filings here, like some small piece of iron powder, it's that small, this looks like a powder here, or very tiny pieces, then if you sprinkle them around this, for example, around the magnet, right, you can see that these iron filings or small piece of iron are going to align themselves around the magnet in this format or in this pattern here, in this shape here. So based on this, we can see that the shape of a magnetic field line, it is going to look like this one here. Okay, so this is how it is going to look like here. This is going to be the shape of a magnetic field line around a magnet, of course. Now, that is one thing here. Based on this, you can see that there are actually more details which I'll be covering in a second, but this is how it looks like, right? So this would tell us the shape of a magnetic field line, and also tells us the strength of a magnetic field as well, because you can see that the closer the line here, by the way, that means the stronger the field, or the stronger the magnetic field at this point here. You can see that the lines are further here, these are more spread. So the magnetic field here, it is weaker compared to a magnetic field in this region here. The reason why, because you can see that, all right, you can see that the magnetic field lines are closer to one another here. If it is closer to one another, that means it is stronger. So we can say magnetic field, all right, is stronger at the poles in here. But there is one more thing here. We said magnetic field lines are a vector quantity, right? That means they have a direction. Do you see any direction here? The answer is no. So what can we do to find the direction of a magnetic field line here? Well, that is also another question then. This time, or to answer this question, of course, we'll use the same magnet, you can say, or the same procedure, but this time, instead of using iron filings, we'll just put some compasses around the magnet, all right? Some compasses around the magnet. And you can do that, of course, both, we can say up and let's say above and then below the magnet. There's one more thing actually I need to tell you, that regarding these magnetic field lines here, it's true that we just drew that up and below, but these magnetic field lines are all over, we can say, all over the magnet in here. So it's just not like the top and the bottom here. It is all over around the bar magnet here. So it is, remember, this is a 3D, so it can attract in all the direction here. Now, going back to this one, what exactly would happen if we put some compasses around the magnet? Then we'll see that normally, or previously we've mentioned that, a compass would normally, like point north and south, right? Because that is how, or what it does, it aligns itself with the Earth's magnetic field line. But if we bring a compass close to a magnet, then we'll see that all these compasses are going to align themselves with this magnet's magnetic field line. So, for example, a compass here, right, by the way, this side of a compass, it is always north, don't forget, and this side is always south in here. So if I have north at this point here, there's going to be south and north attract one another, and this side is north. Obviously, north and north repel one another, right? So it is going to face away at this point here. But at this point here, this is how it looks like, let's say. Right, and then at this point, this is how it looks like here. And then these are how the compasses are going to align themselves around the magnet here. Even below, this is how it is going to align themselves around a magnet here. So now, I believe you have a clear pattern now. So if you, for example, go back to this, or if you just connect or use some lines here around these compasses, just to do this one here, you can see that this would be the direction of a magnetic field line here. So now, based on how these compasses are aligning themselves around the magnet, we can say that the direction of a magnetic field will always be from what? From north to south. All right. And then, of course, we have the same thing here as well. This is how it goes now. So now you can, at any point, for example, you could draw a magnet. If you have north and south, you could just draw a magnetic field line around the magnet with, of course, directions here. Don't forget, these are from both, let's say, up and below here. So based on this, we can say the direction of a magnetic field line is always pointing from north to what? From north to south in here. So that is the fixed information you need to know now here. Okay, now, at any point, what exactly, for example, how do you find the direction of a magnetic field, let's say? Now, like just we've mentioned here, at any point, all right, if you want to know the direction of a magnetic field, at any point, all right, at any point or at any location, that all you have to do, just put a compass at that specific location, then whatever the direction of a magnetic field is, that'll be, or whatever the compass is pointing, that would be the direction of a magnetic field line here. So for example, you want to know what is the direction of a magnetic field line at this location here, and also this location, or this location, or it could be at this location here. So if you want to know, this is what exactly we say by the direction of a magnetic field line at any point or at any location, it is where the needle of a compass is pointing. Babi kama kurdi, I think it would be best. Babi, in order to obtain direction magnetic field line kuwa at any location, then all you have to do is just bring a compass that should be at that location, whichever the direction the compass is pointing, that'll be the direction of a magnetic field line at that location here. Place a compass here, for example, you would see that this is how it points. This is how it looks like. So if you want to know the direction of a magnetic field at any point, bring a compass, Basha, and then just say which direction the compass is pointing. That'll be the direction of a magnetic field line at that point here. Of course, it is a section review, by the way. An Wazari question. It's been in Wazari so many times. We have north and south, let's say, and there are many compasses that are around, let's say, this magnet. It could be these are both up and below here. So, and of course, you can put some letters for these, A, B, for example, A, B, C, let's say D, and then E. We can say F, then you can say G as well. It doesn't matter how many compasses you have, Basha. So, of course, you're given different directions here. Right? This is one of them, for example, and then this is another. And then you could have a direction here, you could have a direction there. You could also have a direction, for example, there. Okay, and then some other directions. Like this one, all right, something like this and this one here. So how do you know which one of these compasses are pointing to the right direction? All you have to do, I would just connect these compasses, or because we've learned already about the direction of a magnetic field line, these are always going from north to south. Just draw the arrows, direction. But those compasses that pointing or aligning itself the same way with the magnetic field line, we can say these compasses are correct. O compasane, they're pointing the same way as the magnetic field, these are correct, and the others would be incorrect. So if you, for example, look at this one here, this compass, we can see the magnetic field line. I should have drawn this one a bit better though. All right, let's see if we can, yes. So here, for example, we could have done something like this, right? These are both up and below, of course. You can see that this compass is pointing the same direction because this is how it goes from north to south, right? These are also true. Yeah, this one is pointing correctly, so this is correct. this one is also pointing correct. What about this two here? These are pointing opposite directions, so C is incorrect. What about this one here? The magnetic field line is pointing this way, but the compass is pointing up. That is also incorrect. What about this one here? This is pointing this way or this way, but this is incorrect as well. This is not pointing correctly, and this one is opposite, so these are incorrect. So you can see the only correct compasses that are pointing the same direction, that would be compass A and compass B. Of course, they can change the place of these compasses. They can change the letter. They can even change these, for example, poles in here, Basha. So how do we know which one is correct? Always draw the line, Basha. Always draw the line, and then see whichever compass is pointing the same way, that is correct. If it is pointing in a different direction, that is simply incorrect. All right, that is regarding, for example, the direction of a magnetic field line of a magnet. So now let's go back through this one more time. With my magnetic field, Basha, it is a region around the magnet where magnetic force can be measured or can be detected. It is measured in Tesla. Basha, that is one of the first things you need to know. How do we see the shape of a, by the way, this magnetic lines, we don't see them. These are imaginary lines, but we can see the effect of these lines here. And Amago, when we spray or sprinkle some iron filings, Basha, the iron filings align themselves around the magnet the way that we just saw, for example. That is the first one, yeah? But iron, there's one problem with that. Iron filings does not show you the direction. It only shows you, for example, how the magnetic field line are, for example, are basically, but not the direction. If you want to see the direction, then you'll have to use what? You have to use a compass. So, Basha. Now, few information we can say, or at least few points regarding this magnetic field line here, north and south. So now, based on what you saw, we can say that the magnetic field lines are, or they appear to begin, watch this, they appear to begin from north and to end at south, right? These are, of course, both, they appear to begin at north and end at south. But in reality, these magnetic field lines have no beginning or no end, Basha. They appear to begin from north and end at south, Basha. But in reality, Basha, there is no beginning or end for these magnetic field lines. Instead, they form a closed loop around the magnet. Closed loop Basha. So if that is the case in here, so this will be the direction of a magnetic field line outside the magnet, right? But what about inside the magnet? It is going to move from these magnetic field lines inside the magnet will be pointing from south to north, because if it is forming a closed loop, that is the only way how they could do that, Basha. Remember this. And then we can also see that the closer the magnetic field lines are, that means the stronger the field, Basha. And based on this, you can see that the magnetic field lines are far from one another around the magnet. But if you look at the poles, the magnetic field lines are closer. The number of the lines are more or higher. So we can see that the magnetic field lines of the pole is stronger based on that. Basha, these are regarding old, or you can say regarding the magnetic field lines here. All right, now let's get back to this and then just go through this one more time real quick. With my magnetic field, or each magnet has two poles, and these are north and south. Normally, sometimes colors are used. Red would be for north, and then blue for south. But these are sometimes used, sometimes not used. These are not, like something that you really have to count on to differentiate between the two. But if it is not, for example, they must, of course, give you enough information so that you can see which one is which. We also mentioned that like poles repel, north and north or south and south, right? But unlike poles, like north and south, they attract one another. And we also said that a compass is a magnetic needle that swings freely on a support, Basha, or once it does, it aligns itself with the Earth's magnetic field line so that it will always show the directions north and south. When we say north and south, we mean Earth's geographic north and south poles. All right, and then also magnetism and magnetic material. We said all type of magnets can attract iron-containing objects like, for example, paper clip, like iron nail, could be anything that contains iron. And we also said that magnets can magnetize. Magnets can make other objects to become magnetic, Basha, like what? Like cobalt or iron and cobalt, and then making these materials to be magnetic or just magnetizing them. And the next thing that we said, it was magnetic field line, right? Or magnetic field in general. We said it is a region, Basha, around the magnet in which, all right, magnetic force can be what? Can be measured. We said the unit for magnetic field is Tesla, don't forget. And the symbol for the magnetic field is B. This little arrow means that it is a vector quantity. It has both magnitude and direction. Don't forget that. All right. So regarding or drawing the lines of a magnetic field, how do we draw the lines? We can use, we said, of course, in order to tell the direction, we can use what? We can use a compass. We can also use an iron filing. But good man, for iron filings, you can see that these are a small piece of iron, like iron powder, Basha, that tiny or that small. If you sprinkle them around the magnet, this is how they can align themselves around the magnet. Well, isn't that basically giving us an idea about the magnetic field lines regarding this, right? So now this is how the magnetic field lines look like. But in order to see the direction, then we'll have to use a compass. Once you use some compasses like this one here, then all these compasses are going to align themselves in a direction, for example, always going from north to south. So based on that, we can say the direction of a magnetic field line, it is always, it is from north to south. Don't forget that. All right, we have this question here also says, how can the direction of a magnetic field be determined? We said by using some, let's say, magnets, or if we use a small, freely spinning or rotating suspended bar magnet, such as the needle of a compass, once you place them around the magnet, then of course they're going to align themselves in the direction of the magnetic field of that magnet, and this is how we can tell the direction. Remember this, with my iron filings can be used to show the magnetic field, but it cannot show you the direction. A few information or a few points regarding the magnetic field. Don't forget, the direction of a magnetic field at any location is defined as the direction that the north pole of a compass is pointing. What exactly this means? Just place a compass there and then see whichever the compass is pointing, that would be the direction of the magnetic field line at that point, and that's it. Basha, second point says what? Magnetic field lines appear, don't forget, to begin at the north pole of a magnet and to end at the south pole of a magnet. But this is just how they look like. Otherwise, there's no beginning or end. Don't forget this. We also have this. Magnetic field lines have no beginning or end. Rather, they always form a closed loop. Basha, if they form a closed loop, because inside the magnet, the direction of the magnetic field lines will always be from south to north. Inside magnet Kenya, we care about the magnetic field line outside the magnet, mostly here. And also remember this, the closer the lines, that means the stronger the magnetic field here. Now let me tell you one thing regarding the magnetic field lines here. From this point on, we might not, for example, draw a bar magnet under this magnetic field line. We might just draw the field line alone instead of using a magnet always. So how do we exactly use or point magnetic field line? Take a look, Baba. But man, at this point here, we could just, for example, draw some arrows here. These arrows, obviously, it will point, that would be indicating the direction of the magnetic field line, Basha. And then if you're given the direction, obviously, that means this is how the direction of the magnetic field line is going. But if you, for example, use one arrow to know which side is, for example, which side is the magnetic field here, or where does it come from? The point of the arrow, north Baba, the other end of the arrow, the end of the arrow is always what? It is always the south here. So, for example, if I have a magnet here, Basha, so we could use a magnet, and this is going to be, for example, starting from what? Starting from, let's just perhaps maybe do something like this here. Okay, north and south, right? If I do some, that'll be opposite here. Okay. Yellow dekak, I'll do this right here. North and south, right? So if we draw some magnetic field lines here around the magnet, this is how it is going to be, right? So didn't we say it is always from north to south? That is how it looks like. But if you draw, for example, if you make the lines bigger and bigger here, right, you could draw, of course, more of these here, right? So this is how it goes. So if you take, for example, some magnetic field lines, I believe that was too much here. So you could draw some magnetic field lines here. So these are always going from what? Going from north to south in here. But you don't have to draw all these lines here. So for example, now once you see this arrow here, that means obviously this arrow is coming from north, or this side of, you can see that it's the same as a magnet here. That means this, if you consider this as a magnet, by the way, this is the direction of the magnetic field here, but this exactly comes from this. You can see that the north pole or the tip, that'll be the north, and then of course the other end is going to be south. All right, that is just, like an information if you ever need this. So the first thing here, good man, one more time, this is how we represent magnetic field line hereafter. These would be the magnetic field line here. And then, by the way, we can use, of course, the coordinate system here. We could use x and y here. So if it is pointing in this direction, that would be x positive. The other way, x negative, of course, it could be y positive, and then it could be pointing downward, y negative too. But there's one more thing here. How about if a magnet or if a magnetic field is pointing into, let's say, into a page at this point here? All right, now watch this one here. Now, considering this, or consider we have an arrow, Basha. We have an arrow. And of course, you've seen arrow, if not at least in movies here. So there's the tip of the arrow, Basha, and then there's the end of the arrow. Now, consider this pen is the arrow here. Now, if this pen is coming, for example, towards you, which part of the arrow do you see? If it is coming towards you, you'll see the tip of the arrow, right? So if you see the tip of the arrow, like for example, in diagrams here, we'll just, for example, write a point here, assuming that this is the tip of the arrow that you'll see. Why? Because it is coming towards you. So for example, now, if this arrow is coming towards you, which part of the arrow you'll see? You'll see the tip of it, right? So whenever you see a point on a paper, on a drawing here, that means the magnetic field is coming out, or you can say it is out of the page, obviously. Out of the page. Basha, consider, for example, this is a page now, right? This side or the upper side is y positive, this is x positive, that would be x negative, and this is y negative below here, just like the diagram that I drew here. But if it is into, for example, let's say if it is coming out of the page, just like this one here, you'll see the tip of it, so you'll see a point. But what if it is going into the page? If it is into the page, you will see the back of the arrow, right? And if you see the back of the arrow, what exactly do you see here? You'll see this cross in here. So if you see a cross, that means it is going into the page, into the page. But if you see, for example, a point, that means it is out of the page. If you understood this, that would be great. Again, I will talk about this one more, so it is a bit early to go through this one at this point here. Just remember this. ذكري magnetic field لو x positive بيتن يعني x negative, y positive يعني y negative. والدشكرية مثلا we have the other component which is z component. If it is into the page, of course, you'll see a cross, but if it is out of the page, you'll see a dot in here, which is going to be z positive. But that would, once again, that'll be for later. For now, just remember this, how we draw or represent magnetic field line. We use arrows to do that, and that's it. That's the only thing I believe, that's the only thing you need at this point. Basha, the next thing that we have is, this one. The next thing that we have is, we're going to learn about, yes, the next thing that we have we're going to learn about the relation between magnetic flux and magnetic field. We have something called magnetic flux. What is magnetic flux and what is the relation with the field? Now, that will be the next thing that we're going to talk about here. So first of all, we have something called magnetic flux. Okay, magnetic. Let's change this one. Magnetic what? Magnetic flux. Okay, magnetic flux, of course, the symbol is, you can say phi with an M here. This M can be capital T, which stands for magnetic flux, Basha. This is a Greek letter, phi, but we never call it phi. We just call it magnetic flux, and that's it. So what is magnetic flux? We can say it is, magnetic flux is the number of magnetic field lines, right? So imagine we have a cross-sectional area, a pipe, a coil, or whatever, right? So this thing has a certain area, right? So the number of magnetic field lines, we were just saying that we draw magnetic field line this way, right? So the number of magnetic field lines that are crossing, Basha, a certain area at a right angle to that area, that is called magnetic flux. I'll repeat this one more time, Basha. So magnetic flux is obviously the number of magnetic field lines, or how many magnetic field lines are crossing or passing, like through an area at a right angle to that area, Basha, that is called magnetic flux. And also magnetic flux, it is measured in what? It is measured in Weber. Right? For short, we'll just call it WB. All right, and of course this Weber can be equivalent or it is equal to some other units which we're going to talk about later. But for now, just remember the SI unit for magnetic flux, it is called Weber here. So one more time, by the way. So now we can, of course, dive into the detail of the magnetic flux here. All right, so once again, what was magnetic flux? That meant the number of magnetic field lines that are crossing, all right, or that are passing at a right angle, not this way here, okay, that are passing or crossing at a right angle to that area here. So let's say we have a few examples. Let's see if I could just make this one nicer here. It's not perfect, right? Perhaps maybe this is a bit better. Okay, so here's, let's just copy this. Maybe making this one that's 2. And by the way, we could rotate this one too. That would be totally fine. So once again, watch this one here. So we said magnetic flux is what? It is the number of magnetic field lines that are crossing a unit area at right angle to that area here, or crossing at right angle to the surface of an area. Okay, so once again, this would be, watch this. These are the magnetic field lines here, right? These are all magnetic field lines here, but we don't have to write all this. You just write one of them and that'll be it, right? So now you can see that these magnetic field lines are crossing or passing at a right angle to the surface of that area, right? Because there's a cross-sectional area here, right? That is what is called flux. So at this point here, we have an equation as well, by the way, for the flux. Well, what is it exactly equal to? We'll say magnetic flux, it is equal to area times B cosine theta. Basha, B cosine theta. All right, that is for this one here. But there's also one thing you need to know. Do you also know that area is a vector quantity? You might say, how? Because perhaps maybe it is your first time hearing this. Yes, area is also a vector quantity. So for example, if this is an area, that is a rectangle, right? So the area, all right, or the magnitude of an area, that would be just the area here, for example, or the equation for area. If it is a circle, the area equal to pi r squared, right? That would be, for example, the area for a circle, that would be pi r squared, yes? That is the magnitude of an area, by the way. Or if it is a rectangle, the area, the length times its width, one, yeah? This is the magnitude of the area. But what about the direction of the area? Direction area, Baba, it is perpendicular to the surface of that area. So isn't this, for example, consider this is a circle when you what surface it is there, right? Remember this, the direction of the area, it is, we'll say it is normal. Normal, it is perpendicular to that surface. Direction area, it is perpendicular to the surface. Perpendicular to the plane of that object, or to the plane, to the perpendicular to the plane of that area. Basha, data, area has both magnitude, it is a vector quantity, which means it has both magnitude and direction. Basha, magnitude, like the value for the area, obviously using the equation we can find the magnitude, but direction area, it is always perpendicular, it is always at right angle, it is always normal to the surface. Kadalan normal, you know that normal yani at right angle, yes? Normal yani right angle. Don't forget this. Yani normal means perpendicular, because now you can see that the angle between the surface and this line here, it is 90 degrees, so you can call it normal or right angle. Now going back to this one here, going back to this, and what is the relation of that with the magnetic flux here? About watch this. I get a magnetic field if they are at right angle, right, to the surface, what would be the direction between the magnetic field and the normal to the area? Aren't these are parallel to one another? And you can even write it here. So now magnetic field, if magnetic field and, for example, the direction of the area, these are both parallel to one another. Basha, if two things are parallel to one another, what is the angle between magnetic field and the normal to the area? It is 0, right? And if it is 0, then cosine 0, that would be what? That would be 1, then we get maximum flux. At the first point here, the magnetic flux, it is maximum. Why? Because you can see that all these magnetic field lines are perpendicular to the surface. رنگ بڵێ مناڵین perpendicular 90 degree باشە why aren't we saying cosine 90 degree بابا ئەگەر لێبی غەڵت مەکە لێرە مناڵین it is true that we're saying it is right like perpendicular to the surface area بس ئەمە هەموو جارێ in order for the angle we'll take in order for the cosine theta باشە ئەمە گۆشەی بینی B و N وەردەگرین بابا like we use the angle between B and N because these two are parallel kata what is the angle between the two here the angle between the two is 0 then cosine 0 that'll be 1 and then we can get maximum magnetic flux at this point here بس ليرة لخالة شديكا what if we're watch this one كاكا أديقر magnetic field كان if they were parallel to the surface of the area if magnetic field lines were parallel to the surface of the area Baba Kati you can see that no magnetic field line is passing through the area right Adio Kati magnetic flux the magnetic flux will be 0 Baba because AB cosine theta when is that what is the angle between magnetic field and the normal to the area we said hamuzare goshe beini b normal wordagrin so the angle between the normal to the area and b is 90 and cosine 90 obviously it is equal to 0 so the whole thing is 0 so at this point if magnetic field line were parallel basha awkati magnetic flux kadakat safar of course we'll need this one the most in chapter 6 but of course since we're going through this already so I believe it would be best if we just started or give you an idea regarding this already yalla baba what if it is neither 9 what if it is neither 0 nor 90 something in between when awkati for example let's say we have some magnetic field lines that are passing through this like some angle here these are the magnetic field lines normally area magnetic field but this magnetic field of course it becomes two component two component like what exactly would they become at this point later the twanin blind component later this becomes what this becomes B cosine and her component that side will become cosine because the hours are like this kata component this is B sine theta مع علاقة مع parallel perpendicular دانية بابا قوشك لقل شيء دابي لقل شان component دابي that side becomes cosine باشا يعني the 20 below the chain نزيك تربيه وش ذكر but I think it's easier to say تماشى بابا so for example this is the magnetic field line باشا this magnetic field line it becomes two component يك شان بابلين بونوعيا أو يديك شان بونوعيا this is because the angle is with the normal يعني it has to be taken with the normal أو component A دبيتا B cosine theta أو component A دبيتا C دبيتا B sine theta استما إيش من بتشاني بابا إيش من B cosine theta يعني وين بتواني بلي the angle بمعنى كذيكا أجر angle كي وقري وليرا ليرا قلت مان if for example if this is the surface area مان هم زاري قلت مان ما أقول شيء ورد قرين لبيني شيء بابا لبيني B لبيني normal كي so that will be what it is that's first بس استا أو component ده تواني بلين لك normal كي component كي ديكا قوش كان يعني بابلين ساينكا قوش لبيني أو component تو إيري دبيتا 90 أو كاتي هيز magnetic flux كمان نبي أقعد لبي كاتا will take the component that is parallel to the normal أو كاتي if we want to find magnetic flux here دبيتا تسي دبيتا A times B أو جدير cosine قوش كي بابا so whatever this angle here you will just write it down then you'll find the magnetic flux طبعا ليرة قلت مان it is maximum it is minimum later obviously it is in between max and minimum maximum نية تسكا قوشة كمان صفر نية ونية minimum يجني تسكا قوشة كمان بابلين نوت نية كاتا somewhere in between depends on what is the angle that is given باشا this is we can say all regarding magnetic flux I'll repeat this one more time with my magnetic flux بابا it is the number of magnetic field lines باشا جماري أو magnetic field line these are crossing or passing at a right angle basha right angle to let's say to the surface and a right angle to the surface of that area to that area basha I'll repeat this magnetic flux it is the number and the number of magnetic field lines that are let's say passing at a right angle basha at a right angle to the air right angle to the area of that surface for that object here that would be the definition of a magnetic field line باشا قلت هم داري قوشك لبيني شو ورد جيري بابا لبيني normally directionي area كو لقل directionي magnetic field كي دوباره دكنا بابا the number of magnetic field lines that cross a certain area at right angle to that area باشا قلت you can the SI unit is Weber باشا but it is equivalent to Tesla meter squared. And then later on, of course, in chapter 6, we're going to see that it is equal to volt second, and also it is equal to ampere ohm second. For now, you just need two things, Basha. This Weber, it is the SI unit, and this SI unit is also equivalent to Tesla meter squared. Basha, ولا شيء بابا؟ ما نقول فلكسك magnetic flux. Basha دكاتة سي دكاتة قلت مان AB cosine ونيا. Yeah, Basha, it is measured in Weber. When you unity area, isn't that meter squared? But what about the magnetic field? Tesla. When this cosine theta has no unity, you can say. So Weber, it is equivalent or it is equal to meter squared times Tesla, and that is what it is. But Weber is the SI unit. Of course, you can also tell. magnetic field دكي وقري ليرة دكاتة سي دكاتة magnetic flux لسر area كاتا توني بلين تسلا دكاتة سي دكاتة ويبر لسر شيء لسر ماتريديزا. That is also possible. This has also been in Uzari as well. And you can always rearrange the equation to find out whichever that you want, or they can ask for it. I got looked down everything. كمان equation كده دكاتة سبابة دكاتة AB يعني بابلين A times B cosine theta. قد قوش لقى دابو باشا قلنا قوش لقى دانا بو هالبيزناكا كوساينكش بكار بيني بس بوشة تدي magnetic field line كان تبي perpendicular بالنسر surface دوباره دكا مو غلط ما كبابا رنگ قبل ما وصل perpendicular هذه اللي برسي why weren't using 90 قلت ما هم زاري ما انجلي بيني magnetic field دكا ورد green لقل شيء لقل بابلين directionي normally area كي بابا اللي تيجنا تسيتن ليه اگر magnetic field line که perpendicular ولا سر area که دبیت maximum اگریش قلت من parallel بود دبیت صفر اگر گوشش بود لبینی max صفره. هشتش دي كمان يبقى بشتري بس ما كتبوا قلت من the intensity of a magnetic field is larger at the poles when magnetic field كل شيء stronger like it is stronger because at the poles obviously. Why? Because the magnetic field lines are closer there Basha. If the magnetic field lines are closer, that means the strength of the magnetic field is obviously stronger. Now we have another thing, and that is called magnetic hysteresis بابا. ليرة تونبل magnetic hysteresis what is magnetic hysteresis? If we place let's say let's say what is it called? A ferromagnetic material basha, like a piece of soft let's say a piece of soft iron basha. Cut 20. If in Uzad, of course, they might ask you, for example, what is one example of a, let's say, ferromagnetic material? You can say a soft iron, basha. And there is a reason why we call that ferromagnetic. Because it can be magnetized very easily, and of course, it can be demagnetized easily. Just remember this. When a ferromagnetic material, like a piece of soft iron, if it is exposed to a magnetic field, then it becomes magnetized. So this is, we can say, the core of magnetic hysteresis. There is a little bit more you need to know, Basha. It's that, for example, we have a magnet, Basha, and we said in magnets we have north and south, Basha. All right, so if we have a small piece of iron, soft iron, obviously, if we place this, clearly there's a magnetic field around the magnet. Where? All right, so if this iron it is exposed to this magnetic, magnetic field this iron becomes what? It becomes magnetized. the beta magnet. باشا يعني أو iron بابلاتش the beta babbling north like the beta south. All right, so that it would always be, for example, in a way so that I get iron كلير دابني بابا أو كاتير the beta south so that they can attract one another like the beta north. باشا, this is obviously what happens here. بس we call it as we can say that the flux density باشا and the change in flux. What is exactly the change in flux? The number of magnetic field lines that are crossing bubbling in the unit area at right angle to that area, Basha. That crosses the unit area right angle to that area. It's called magnetic flux. The change in magnetic flux, for example, for this iron, Basha, changes non-linearly with the applied field. For example, once this iron is inside the magnetic field, then this piece of iron slowly becomes magnetized. So that even when this magnet is removed here, Basha, and now there is only the iron that is left in here, Basha, this iron retains, keeps part of the, for example, magnetism that it became here. قلت man iron كبو magnet one, yeah. Even after you remove the magnet, بشكل magnet اللي now iron كده منيته بابا. This is what we say by part of the magnetism will remain inside the iron basha, and that is what is called magnetic hysteresis. قاعدة توانبلين magnetic hysteresis. It is bubbling, the lagging of a magnetic field bubbling inside a piece of iron. That's basically what it is, basha. قاعدة دوباره دكنا بابا. Gutman, when ferromagnetic material, piece of soft iron is exposed to a magnetic field, it becomes magnetized. Is this. The magnetic flux density increases, let's say, or increases non-linearly with the applied field. We can say when the applied field is removed, that piece of iron keeps part of, or we can say retains part of that magnetic field in, let's say, inside itself. يعني بمعنى كذا أو iron هذا بيتيان بابلين, it is still magnetized. It's still a magnet even after you remove the magnet, but not for a very long time, by the way, temporarily, basha, only for a short time here. Then this phenomenon is what's called magnetic hysteresis, basha. And then this, of course, this process follows a curve, basha, curve كبونوية. بزول بسعر بابلين لكتابك نيدا بابا, so you don't have to worry about this one here, basha. Then this curve, for example, of a magnetic field versus magnetic flux is called hysteresis curve. Basha وتنها لو زاري اللي راحتي تو بابا تنها بتواني بلين بروسكية, which is the magnetic flux density and bablin nahar. Tawani bono play is when the magnetization of a material lags behind what? Lags behind the changes in the applied field, resulting in a loop shape that becomes that is what is called magnetic hysteresis. Basha loopakash, it is called magnetic and bablin hysteresis loop. Oh khali that one in blend khali domu khali dom simzana baba. That'll be the definition, and that is the only thing you have to know at this point, nothing more than that. Basha sta section review baba persarana so gringa agad libi hariglo persarana tsamdin zalo zari hatino. Basha. All right, it says the first question that we have says when a bar magnet is broken into two. We have a bar magnet. This is broken into two pieces. How many poles would each pole Basha have? Every single piece will always have two poles. We can never have less than two poles Basha, for a magnet. All right, now interpreting graphics. All right, says which of the compass needle orientation in the figure might correctly describe the magnetic field at that point here. Basha Gutman. To answer this question is all you have to do is just draw a magnetic field line here. So now all you have to do is just draw a line here. And this is how it's supposed to look like. When these are both, we can say above and below, or just around the magnet, let's say at any point. At this point here, magnetic field it is going from north to south. Why? And then of course here as well. Let's start from A here. Is A pointing the right direction here? You can see that this is the direction for the compass A, so A is correct. What about B here? That is also pointing the same direction, so B is also correct. What about C? My magnetic field this one is pointing up. Kata, is it correct? No. What about D, Kaka? This point is supposed to point this way, but our compass is pointing the other direction. Kata, this one is also incorrect. What about E? Magnetic field later direction compass Kata, this one is also incorrect. What about F in here? F is also incorrect because these are opposite direction here, so this is also incorrect. The only two correct compasses that show correctly the direction of a magnetic field, that would be A and B. These are of course bin and Uzari. Before Uzari, chapter V questions. What is the minimum number of poles for a magnet? It is always two, and these are north and south. We can never have less than that. When you break a magnet in half, how many poles does each piece have? Each piece would always have two poles. We can never have less than that. It is also related to this, Baba. I mean, it's a bit actually different, but it is still related to these kind of questions. So let's say, why does a very strong magnet attract both poles of a weak magnet? Let me give you a little info regarding this one here. Basha, we've mentioned that when we have magnets, all right, Gitman north and north, and south, let's just make these perhaps smaller. Gitman north and north, let's just make these north and north, they repel one another. What about south and south? They also repel one another. But what if it is north and south? If it is north and south, they attract one another. These two attract one another. So the question says, why does, for example, a very strong magnet can attract both ends of a weak magnet? What exactly, or why does this happen? Consider we have a very strong magnet. Here is a very strong magnet. We have north and south. First of all, if it is not a magnet, if we have a piece of iron, it can be attracted to both ends. It doesn't matter if it is south or north, right? All right, so if it is a piece of magnet, it can be attracted to this end. And of course, you can, for example, just detach it or just take it off here. And then it can be attracted to this end as well, right? But what exactly happens here? Basha, if we have another magnet, all right, but if this magnet is weak here, both ends of this, of course, or you can say that both ends of this magnet can be, or you can say that both poles of these strong magnet can attract, for example, the weak magnet here instead of repelling them. How does it happen? Now, in order to understand this, of course, I need to give you a little bit of information regarding this. Rasha? Now, inside magnets, of course, you can see that if it is a strong magnet here, now we know that it comes, or this magnet comes from something called domains, right? So what are these domains here? You can see that these domains represents tiny magnets inside a magnet, right? And each one of these, of course, you can see that once it is a magnet, all of them are pointing in the same direction here. Now, these smaller tiny magnets here are called domains here, or domain for one, all right? So what exactly domain, or where do they come from? When we have elements or atoms, let's say, all of these atoms have the same, let's say, spinning or rotation, then this produce, let's say, these atoms or a bunch of atoms or molecules produce a magnet here, because due to their electron spinning in one direction here, so they produce these tiny magnets here. So this is a domain for a bunch of atoms. This is also a bunch of atoms and all that. If it is a magnet, all of these are pointing in the same direction. All right, but look, if we have this weak magnet here, that also has domains too, by the way, Basha. So, but the domains of these weak, by the way, let me not forget in here. So these domains, obviously, this side is going to be north, Basha, because all of them are pointing in one direction, and we've mentioned that earlier here. Each one of these produce these are small magnet, and you can see that the hour is north, the other side is south in here. So north and south, north and south. So you can see that all of these are, or you can say at least the magnet outside here, they produce, let's just call that this side is north, and then the other side is south. And of course, it's the same thing with this weak magnet, by the way. Okay, so let's say this is the weak magnet here. These domains are, all of them are pointing in the same direction, let's say. But look, this magnet has a magnetic field around it, yes? There is a magnetic field around it. And this, because this magnet is very strong in here, so the magnetic field is always from north to south, right? So now, once this weak magnet, this is the weak magnet, by the way. Weak magnet, right? So this weak magnet, it is exposed to the magnetic field of a stronger magnet. Now, this stronger magnet, it is going to realign these domains of a weak magnet. Let's say, even though this is written north and south in here, but it can realign them. Just like, for example, if this is a compass, the magnetic field would realign the direction of a compass in here. So in this case, we can erase this one now. And we can say that these magnetic domains are going to be realigned. If that is the case, this is how it is going to realign them now. Even though outside the magnet, this side is written north and the other side is written south, right? But the domains inside the magnet are being realigned. If it is realigned, obviously now, you can see that inside the magnet now, or you can see that this side becomes the north and the other side is becoming south. And then you can see that north and south are attracting one another. So if you bring this magnet here now, So this is the north side. If you just bring this one here, this north, of course, it is going to be attracted to this south right here. Even though on let's say the label of the magnet, it might still be written south and north here at this point here, but it can, because this strong magnet, it just realigned the domain of this magnet. What if you, for example, bring this magnet close to this end here, just like we said, for example, it can realign the domain of this weak magnet. Now, all of the domains are going to be pointing in this direction so that no matter which side of a magnet you bring close to one of the poles, it can always realign that so that it can attract this weak magnet to the strong magnet. Now, let's say this is the north side and the south side of here. What happens if you flip the magnet or reverse that, for example? Let's say on the magnet, this side is written north and this side written south. But once you bring them here, right, even if that is the case, like for example, first the domains are aligned like this, but because of this powerful magnet here, it can realign the domains of this magnet. Now it can flip the direction here. It changes the direction like this. If it can change the direction like this now, inside the magnet, this side becomes south and this is north. Now south and north can attract one another. So now the reason why a strong magnet can attract a weak magnet, the answer to this question is because this strong magnet, right, it is, or the magnetic field of this strong magnet dominates, Basha, and it can realign of the domains of a weak magnet so that no matter which side of a magnet is brought close to one of the poles, it can always attract that. And you can say that it makes this one behave the same as if it is a small or piece of iron. So no matter which side you bring this magnet close to this, it will always realign the domains so that it can always attract. Here's the answer one more time. We'll say the strong magnet's field dominates, because obviously it's stronger, realigning, Basha, realigning the weak magnet's domain, with the domain it can realign bibna, so that the closest side it has always become the opposite pole, so that it can always attract one another regardless to what is the label on the magnet here. And the Prasadi Uzari, and that'll be the end for this session, Baba. What is the minimum number of poles for a magnet? Gutman minimum that. It is true. When you break a magnet in half, how many poles does each piece would have? That'll be 2 again. A region in which a magnetic force can be measured. It is a region, Kaka. If it is, whenever it says that is a region, that is a magnetic field. When and you can see that it says magnetic force can be measured. That is a magnetic field here. All right. The unit for measuring the magnetic field in SI system, by the way, if it is magnetic field, it is Tesla. Tesla, obviously, it is equal to some other units, but because it says SI, so only Tesla is the SI. Otherwise, Tesla is equivalent to some other units, but we don't need them. 5 says is the number of the magnetic field line that cross a given area, which is normal, let's say in the normal direction, that is a magnetic what? That is a magnetic flux. It says number of magnetic field line that cross at right angle. Divided by the SI unit of a magnetic flux, it is Weber. The better SI unit, Baba, because it mentioned that it is equivalent. Weber, it is equivalent to other units. So, but once it says SI, so there's no more than one, because there's only one unit that is SI. And then we also have this one, Tesla times meter squared, Baba. You can change these words into letters here. That is Tesla times meter squared. What is this equal to? Isn't that Weber here? Yes, because magnetic flux. They got AB cosine, that's one, like B times A, doesn't matter. Cosine B Tesla, Tesla times meter squared, that is going to be Weber, which is a unit for magnetic flux. And then the unit of measuring magnetic flux, all right, what is it equal to? This one here says, obviously it is Weber. What about Tesla? No Tesla. What about Tesla meter squared? And then we have both A and C are true. Lira does not say the SI unit. When Madam does not say the SI unit, so kata Weber, it is true. And also Tesla meter squared is also true, kata. We can say it is both A and C. And then this one, of course, you can see for later, because some of these units are related to chapter 6. So we're just going to leave this one at this point right here. That'll be the end for this session. Inshallah, next time we'll talk about magnetism from electricity. Like how can we generate or induce magnetic field by using electricity, right? That'll be for the next session. So till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.